So we can learn that from our coefficient of determination. Which brings us to our next bit, which is our least squares regression line, which is pretty much a mathematically exact line of best fit. It's not just roughly drawing in a trend line, it's exactly figuring out what line best represents the overall pattern of my data. And the reason how it technically does that is by minimizing like the sum of like the residuals, which is really interesting. But again, won't be going into that today. And it's usually in the format of y equals bx plus a, where y is our response variable, b is like the slope or the gradient, x is the explanatory variable, and a is the y-intercept. If you've ever wondered like what the y-intercept means, it's like literally referring to the y-intercept. So if we extended this trend line, the y-intercept is where this line would intercept the y-axis. And because of that, mathematically, whatever our y-intercept is, it's always, always, always when x equals 0. So if you ever need to find the y-intercept, and you know, like if you have values for y and x that you could use, you can just say let x equal 0, and that'll tell you what your predicted y value would be for when x is 0, which would give you your y-intercept value. So that's really important to keep in mind. Or if you know, if you know any 3 of these points, you can actually mathematically figure out the last, just like with any formula. So that's a quick overview of our least squares regression line. And because we have this least squares regression line, or this trend line, we can actually use that to make predictions by substitution. So if, for example, you know the y-intercept and you know the slope, and you want to know what y is, for example, when x is 4, you can really just sub that straight into the equation. So let x equals 4, solve the equation and see what y would be, which would be this point about here on the line. So it would probably be something in the low 20s. That also kind of brings to an interesting distinction between interpolation and extrapolation. So have a think about if you remember the difference between those two. So interpolation is when we're making predictions within the given data set, within the range of values that we know, but extrapolation is when we're making predictions that go beyond the data that we have. And as a general rule, something really important to remember is that interpolation is always more reliable than extrapolation. Because interpolation, we've got this data, we've calculated this trend line based off this data, but the danger is with extrapolation is we actually have like no way to know whether this pattern like continues on beyond the research that we've done, because most linear patterns don't go on for forever. For example, with my car example from earlier, if that linear line pattern kept going, eventually a car that had driven a certain amount of kilometers would be free, or even like $, which just doesn't make sense. So that's the danger of extrapolation. It can kind of like give us values that just aren't reasonable or possibly aren't even possible. So that's the danger with extrapolation. And also have a go at see if you can identify where the residuals are on this graph. Our residuals are these distances here. So the residual is the vertical distance between the actual data point and its predicted value from the line of best fit. So this would be our residual value here for this point here. So linking it back in again to what we were saying earlier about our R value, with our R value, we were saying that it's only appropriate to use a Pearson's correlation coefficient if it's linear, but it's also only appropriate to use a linear trend line if it's got a linear relationship present. So how do we know if